Okay, and let me get back to my share again. Just bear with me here. For some reason, it's not showing my screen. I can't see it. I just see participants. Let's see here. Let me stop share. Huh. Well, any ideas? Let me see. Oh, there it is. Okay, I got it. It's always a button you have to push, right? Okay, well, I'd like to welcome everybody today. Just so there's no confusion, we'll have to go through and clean this up a little bit. We're doing two things. Number one, we are cleaning up the email list simply because the group started very, very small and I got larger, and we're constantly added more folks. I'm here at a AI conference at Stanford University, and there were quite a few of my colleagues that are just really in the estimating field, that are doing some amazing work with AI as well, by the way, that want to be part of the group. So one of the things that we'll need to do, and Anne, maybe you can help me do this, is we'll clean up the email list to make sure we have the folks that that are on the list that still want to be part of the group. And just so there's no confusion, and to clarify, there's two groups. One is the core group, which is not mandatory that you make every core group meeting, but we ask that you make as many as you can. It's just 30 minutes. It's a check-in. We've been having very good, productive meetings. And of course, if you miss, that's no problem because we record the meetings. And then a monthly meeting at the very end, the last Friday of the month, which is an expanded meeting, which is 60 minutes. And so you may have, if you're in the core group, you've confirmed you're in the core group, you'll have two invites, and we'll clean that up. I just didn't want to take the I didn't want to cancel one meeting and make there be confusion. So or to create confusion. So just know that that will be combined into one. The core group's only the first 3 Fridays of the month. Um, so it's good to see everybody today. And I'm at UC or Stanford University, and as I mentioned, on the medical side of the delivery, and there's 200 of our fellow colleagues here in estimating and design and construction, and it's just great to see the great work that the industry is doing to even embrace technology. And I was reminded how blessed we are, and how what a great opportunity we have in this group to be collaborating with great thinkers that are solving such an important problem challenge. And I'm also reminded today, as presentations were uh, being delivered, on how truly advanced, what a challenge we're addressing, but also how advanced collectively our thought process is. And so it was just a great validation, I guess, today. And there's definitely a lot of learning today. So I don't want to spend too much on the upfront. So what I would do is just a quick update on the paper. There are Rivka's paper, who she'll be presenting today on her paper, and I'll introduce them separately. Um, that has gone to review, and Jennifer Taylor, your paper has gone to review as well. And And then the next up is Dr. Vashish Singh, and Dr. Brad Hyatt is up is next up. So stay tuned if you want to be part of the review process, the technical review, which is kind of a peer review. That's where you would want to be in the core group for that. Okay. Um, the first review that happens is Dr. Jay Lunn at University of Davis. He has over 150 scientific papers published, and he's taking care of the first preliminary review to make sure things are on a good level, and then it will move into the technical and peer review. So we have two presentations, and I won't spend now too much time walking through this here. Let me see, dynamic engineering model, master theory walkthrough. Okay. It looks like I have two agendas that are kind of combined. We're going to start with our first presentation which is Ireland Brown. She's from MIT. She's a PhD candidate. When she was doing her master work, I was entered, by the way, I was introduced to Ireland by Steve Furr. And Steve has a knack for connecting people and intellect. And it turns out that her work is very relevant to our early process. And I want to show you, let me see if I can forward my slide. And for some reason, it's not forwarding. There we go. Can you see the next slide? It should look like a process map. Yeah. Yes.
Yes.
Okay. Thank you. Um, so and again, if you don't uh, get all of the nooks and crannies of it, that's okay, because we haven't presented this at the big group yet, just at our core team. This is essentially a process map of an extreme estimating process. And again, the goal, as we all know, is absolute minimum variance to predicted state. And so the whole process is on a timeline. And the beginning is technology being developed, and as the project itself, a mission project, starts to be developed, so too is the estimate at the very, very beginning. And there's integration all the way through. We call it a two-way data flow. And so today you're going to hear from two perspectives, which are, I feel, very important in the process. So what the first presentation will be from Ireland Brown, again, MIT PhD candidate, and she'll be presenting on predictive modeling on the resources needed very, very early. And then second will be Rivka uh, Malik, and she will be presenting on moon excavation. But what are the things we have to think about as we're predicting what production will be, even as they're inventing the technology? So it's not an afterthought. And what I like about both these presentations today is it starts to dive into how the estimate will connect to engineering modeling and digital twins and predictive production modeling and things of that nature. And as last week at our core meeting, we determined that one of the biggest gaps we have in the theory is that interconnectability of the master estimate being the clearinghouse, and how it talks to these models they're produced. And we have to understand or consider that models can only move so fast. Typically, estimates can move faster. So the direction of flow is going to be very important. So I wanted to hone the team in as far as when you hear presentations that are a piece of presenting a piece of their work and their expertise and how it fits into the master estimate. The master estimate theory is a framework, a highway, if it will. And so each person that is writing in the paper has their expertise. So it's, if you will, it's an off ramp from the main theory, and then they go in there. Then they're able to move in their expertise, but it has to align and conform with the master estimate flow. So. So just so you can see kind of where we are on the timeline here of the process. So I'm going to escape here and I'm going to stop share. Screen sharing, okay. And then just let me set up, let me see here. Okay, I believe you should be able to share. So I'd like to thank Ireland Brown, again, a PhD candidate at MIT. You can maybe just explain a little bit about your work, and you and I have had a pretty productive conversations about the relevancy of the work you're doing, and we've shaved the scope to fit within the master theory. So without further ado, Ireland, tag you're it. We're looking forward to
Awesome.
hearing about your work.
Yes. Thanks so much for the introduction, Paul, and thank you to the team for having me today. Paul has spoken very highly of you guys, so I'm happy that I get to know you guys and work with you. I see it says host disabled attendee
Oh,
screen sharing.
well, that's interesting. Host, well, remove. Uh, well, that's interesting. Remove from share screen. Well, uh let's see here.
Oh, you want to give me co-host permissions and I'll try and
Yeah,
fix this?
sure. Thanks, John. Let's see here. Well, I'm looking for
Just right-click my
co-hosts
name.
now.
Right-click my name.
What's that?
Right-click my name and say co-host.
Oh, okay.
See, Anne's having a laugh.
Let's see here. Chat.
It's just
Okay. You're now host.
Okay, let's see. All right, looks like I can share. Thank you guys. Go ahead and pull this up. Can you guys see my slides?
We can, yes.
Awesome. Okay, cool. So, yeah, I've had the pleasure of chatting with Paul a couple times over the past several weeks after I presented at the Lunar Surface Innovation Consortium hosted by Johns Hopkins. They did a meeting about lunar ISRU, and Steve was able to introduce us, like Paul said. And so I'd like to share with you guys a method that I've used for some of my work here at MIT. And I've titled this presentation Mapping Mission Demands from Modeling and Simulation of Space System Operations to Cost Estimation, which I know is where you guys are really the experts. So this has come out of some work that I did during my master's thesis studies. The title is Cost Optimized Logistics for Commercial Operations in Low Earth Orbit and Cislunar Space. I've published 3 papers from this, so I'd be happy to share that with you guys if anybody is interested. But you'll see here that my principal investigator on this work, Ollie DeBeck here at MIT, his group here is called the Strategic Engineering Research Group within a bigger, broader group called the Engineering Systems Lab. And what he's been primarily interested in over the past several years is space logistics and supply chains for maintaining steady state operations of some of these new commercial vehicles or commercial space stations, whether that's in orbit or on the surface of the moon. There's also a lot of people here doing work looking into logistics of stations on the surface of Mars. So really getting into how are we enabling these things to operate and what do we want to get out of it? So I'll go ahead and get into this. So the biggest question that Paul was saying that you guys have had in the back of your head and what I've read in some of your meeting notes is how can we measure the time and resources required to sustain a space station? And when I say space station, I mean anywhere in space, like I said, in orbit or on the surface of the moon or on Mars. And how can we map, the whole purpose of doing this really is to be able to map those into your estimation techniques. And there were 3 big steps to doing this that I followed in my work, which was first, the mission architecture design. So getting a solid baseline concept of operations for commissioning this station, meaning like delivering all the pieces and parts to the location and assembling them, as well as the steady state everyday operations. And then the second aspect is
Ireland.
Yeah, go
my
ahead.
apologies. I want to put context, and my apologies. I didn't give context because this will help the participants. Think about
Yeah,
the
sure.
estimate at the very beginning. This is for the attendees. Think about the very beginning of the estimate where the structure of the estimate, the line items. What does the estimate actually look like? What are the line items? How are they broken out? Things of that nature. Of course, AI tools are going to help certainly, plus experience. But this is an area that is very relevant to Ireland's work. So sorry, that was my fault. I should have given context, a better context before you started. This will help down the road. Thank you.
Totally.
I appreciate it.
Yeah, no problem. Thanks for that, Paul. So the second part of this is identifying what elements are needed to perform the mission events. And by elements, I mean the launch vehicles, crew modules, lunar landers, ISRU systems, anything like that that's actually performing some sort of operation within this mission design. And then the third one is what do the elements themselves need in order to carry out these mission events? And what I have written here is that both crew members, so our astronauts, and the vehicles or systems like an ISRU system, and for just to be perfectly clear, ISRU meaning in situ resource utilization, like an oxygen generation system deployed on the lunar surface. Both of those things need resources to perform tasks. And then some elements produce resources, like the ISRU system, for example, as outputs, while others can produce waste, humans throwing away trash, and that must be managed. And the hardware themselves require maintenance, so you could consider maintenance as a consumable resource or something that the elements demand, since those have to be carried out at some regular rate based on their operational lifetime. So to keep going on with this question, resources and maintenance are, like I said, consumed at these specific rates. And so, for example, there are a few things that we know. For an astronaut, we know the human metabolic rate. There's a paper out there called Astronaut Mass Balance, which is used for crew logistics on the ISS. And we know the transportation vehicle volume and the length of the mission that we're looking at. We also know when it comes to the system, for example, the Environmental and Crew Life Support System, or ECLSS, the efficiency of how much they can recycle oxygen from carbon dioxide in the air, without getting too technical. And with these known values, we can compute how much food a human needs during a mission, how much oxygen has to be delivered for this ECLSS system, how much can be delivered in one launch by the transportation vehicle. That's where the volume and mass constraints come in. And then how many resupply missions are required based on all those constraints, and where do the resupply missions need to go? Because if you're going to the moon, the crew is going to consume certain resources in Earth orbit, and then they're going to need more resources when they get to the moon. So this is just a high level example of this. So now I'll start getting into some more specific examples of these things. And I also want to show you the tool that I used to compute these things, because computing it by hand can be quite laborious. So for example, if you could consider a concept of operations for delivering and operating this lunar oxygen generation system. This is just my initial draft of what it could look like, where we use a Starship, for example, rocket to deliver this system with astronauts to the lunar surface to commission the system. The astronauts return from the surface, and then over a certain period of time, resupply missions are needed to keep the system operating. And so with this, what I also do is identify a feasible set of these concept of operations. And what I do is iterate on a certain set of decision variables, and this is completely up to the designer to iterate on. Most of these are logistics-based, like the container specifications. Are we going to have a stockpile of resources at the lunar surface before the crew get there? Things like that. And then, like I said earlier, the demand rates of all these elements involved. So how much oxygen, how much food is an astronaut consuming per day? And then same for the system itself, how much resources does it need? This could be power. I specifically looked at the reduction agent for the system in order to operate. And so getting into the modeling tool aspect of it, I used SpaceNet, which was developed by Paul Grogan. He worked with us here at MIT. He's now at Arizona State University. And this is a discrete event modeling and simulation tool, which is able to output the mass per resource, per container, per carrier throughout that accrues throughout the mission. And it identifies a feasible mission scenario as a mission design that supports the demands of the elements. An infeasible scenario would basically mean that mission critical demands are unmet by the current design, and you need to go back and restructure your ConOps or supply chain design in order to meet those needs. And so the outputs can then be organized however best fit into your estimation technique. The way that I did it was I organized it by crew dedicated versus system or hardware dedicated resources. And then also further by launch event in order to compute the overall resource costs, labor costs, and then transportation costs that accrue during the mission. And this is just another nice to look at overview of how it works. But I'll quickly show you guys the actual application here. So this is SpaceNet. And you'll see we have these yellow sort of trajectory looking things. And then some dots in various locations. And what those dots are the nodes during the mission. So these are all the locations that throughout the mission, each vehicle is transferring to and from and things like that. And the inputs to SpaceNet, we recently developed where we can do pretty much everything in Excel here, which makes it really easy for us to iterate on designs. But we manually put in all these nodes, the edges, which are the trajectory between each location, the resources that are involved, so water, in this case I was doing the Lunar ISRU, so regolith, hydrogen gas, liquid oxygen, and then even food, clothing, trash bags, spares for the maintenance aspect of it. And it records, what environment do these things need to be stored in, what's the unit volume, the unit mass, and then you'll see here it says class of supply. And that organizes things by resource state, so gas, solid, things like that. And then you describe the elements that are involved. So I have the carbothermal reactor system, that's the ISRU system. I have Starship, the launch vehicle. I have Orion, which is our crew carrier. And then I have crew member as well as containers and things like that. And I can define the mass capacity of these things, the volume capacity, the maximum crew that things can carry, the mass of the astronaut, again, the environment that they have to exist in. And you can define or not define these things as desired for whatever it is that you're trying to narrowly or widely analyze here. Let's see. And then this is where I implement those demand rates that I was telling you. So for example, crew consumption. So this is the water consumption rate in terms of kilograms per crew member per day, which you can get from like an astronaut mass balance used for the ISS, and which is just based on the metabolic rate, as well as other things they use like hygiene materials, clothing, trash bags, waste containment. And then I have system-specific demand rates. So this Sabatier model, that's the chemistry that goes on inside the ISRU system, as well as ECLA systems, which track, how much hydrogen gas is needed for this system to operate, how much water is it producing, how much methane is it producing, and all those things. And then in the missions tab, this is where you put the concept of operations. So this is probably the most challenging and laborious initial part of all of this is adding all this in, because it gets down to very specific timing and everything like that. But the pro of that is that you really get to track things down to as low of a level that you guys are looking for in order to improve the fidelity of your output. And once you do it once, iterating it is not as much of a challenge. So you'll see here I have the pre-positioned supplies, launching Starship and then refueling Starship in low Earth orbit, a resupply launch, and you can turn on and turn off systems as well. So I want the system to start consuming resources at this time, and that way it tracks it for its specific on and off times, as well as when astronauts are involved versus not being involved. And then I can load it into here, and it'll show me a bunch of different data displays. So this will show me how much resource mass is on each leg of the mission. You'll see like I have all the nodes here on the left-hand side, Kennedy Space Center, low Earth orbit, lunar South Pole, NRHO, and then the dates at which these things are occurring. And then the most interesting tab is this one. So this is the manifest tab. And what this does is this is where it computes the total amount of resources based on how I've defined my demand models that are needed throughout the mission, and also where they're needed. You'll see like here on supply edge, Kennedy Space Center to CTR, which is where the ISRU was placed at the lunar South Pole. And it puts them into these containers and onto the carriers that are involved in the mission events, like I had said earlier. And it'll basically tell me, are there enough, resupply missions, or is the carrier big enough such that the resources are able to get to where they're needed, when they're needed throughout the mission. And so this not only gives me the total number of resources needed throughout the mission, but also if my mission design itself is feasible. So I know that was a lot. And then this tab, this is like the full simulation tab. So this is where you can really troubleshoot, where are there insufficient resources for certain things and how much of it is. And the last thing I'll share with you is that this information can then all be extracted into an Excel sheet, and it'll show you, like, for each launch vehicle and each carrier, how much oxygen was in one container, how much food was in another container, in a chronological order throughout the mission, which was very, very useful, and the primary input for my cost estimation model, and I think is what Paul thinks would be the most interesting part, or maybe useful part for you guys. So I'll stop there. Happy to take questions, and yeah, thank you so much, guys. I'm happy I was able to share this with you today.
Great. And we'll open it to questions because we have Rivka starting next. Yeah, outstanding. I think we can see the sense of the complexity of even putting an estimate together that's relevant. And I've said this before, but I'm going to say it again because we have new people. On Earth, when we estimate, we say, you don't need to count the screws. But remember, in lunar estimating, we not only count the screws, we will need to count how many times we turn the screw. Because of the extreme condition. It's extreme estimating. So with that, outstanding job, Ireland.
Thank you.
Let's open up to questions. We've got 5 minutes for questions. Steve, I'm going to pick on you.
Yeah, I've already asked her some of my questions. Really, I thought the oxygen generation return on investment research was highly relevant to this as well, though maybe a bit removed from the actual cost estimation. But just how interrelated everything was.
Yeah, I agree. And, my mind as she was presenting kept coming on, the means and methods and general requirements that, that we have to figure, and every piece and nook and cranny that is used in construction or to support astronauts or the lunar base needs to be accounted for. It has a cost to it. It has, and does it really make sense to have an estimate that's 90% complete? It should be, I would argue, it should be 100% complete, 100% prediction. But I thought, it's a good way to articulate the complexity of what we're faced with. Because if we can imagine this, we want in the theory anyway, we're pushing for the estimate to be in front of engineering models. Of course, there's constant adjustment, of course, but to have all these accounted for instead of waiting downstream to find out what all the resources that are needed, what does the estimate look like? How is it structured? And that's a challenge.
I think Vishesh has a question.
Yes, thanks. Vishesh?
Yeah, I think before me, Ivanka had their hand raised. I don't know if you want to go first.
Oh, sure.
Oh.
I did come in a little bit after the presentation started, so I may have missed some of the assumptions that were discussed in the beginning. Was curious about the events piece, the extreme events that can occur during a mission, and whether these were sort of captured in some of the scenarios, sort of as bookends for what
Yeah.
could potentially happen that can impact the costs. Thanks.
Yeah. So I didn't show it in this demonstration, but there in one of my papers that came out of this work on commercial space stations, part of that decision vector that we were iterating the mission operations on was there were 3 contingencies that we looked at. And it was a delay and resupply, a completely missed resupply, and then I think I can't remember what the third one is, but those were things that we iterated on for our trade space of scenarios that we ran through here in order to observe that like sensitivity to overall feasibility, being able to get resources where they're needed, but also just in general the amount of resources that are needed and how that the implications on the overall cost. So contingencies is definitely something that can be incorporated in this type of modeling. And in this one specific, things that I saw through my iterations were huge sensitivities on systems that require a lot of gaseous commodity to operate. So for the Lunar ISRU system, for example, if you're using, let's say methane as your reduction agent, how much methane is it consuming to produce oxygen, and how you deliver that methane, and when you deliver that methane is, it was a huge toggle in feasibility. I actually ended up getting, within my trade space that I looked at, Starship was the only one that was able to enable a feasible mission, and my representative Blue Moon style lander and smaller were not able to deliver as many resources in time in order to meet the output requirements of the system.
Yes, one of the other points to be cognizant of, this is for the team, is that through verification process engineering models and predictive modeling, verification meaning that you have a almost real-time tracking of where everything is in the mission, and they're running scenarios. And so if there's an incident that occurs, it calibrates new probabilities, not just one, but several models. So I think it's addressed in several different directions. So it's not just one solution to many different types of points of reality that could happen. I hate to do this, but could Vishish, I need to move to Rivka.
I can ask a question in chat, and
that'd be great. Ireland, thank you so much. That was just outstanding.
Yeah, thank you
guys. It's congratulations on your PhD candidacy at MIT, and you're going to do great things in life. I know that. Okay. So Rivka Malik, she leads major estimates on large scale civil and site developments. She's a certified professional in sediment control, and also a professional certified estimator from the American Society of Professional Estimators. She wrote a very great or a very fun and informative paper on tracking how we would track production on moon excavation. So I'm looking forward to her presentation as well. So Rivka, tag, you're it.
Yes, let me just see if I can share my screen here. It says sharing is not turned on.
John,
Paul,
are
if you give me co-host permissions, I can fix this. Just right-click my name and say make co-host.
Oh boy. I'm just wondering why, because I already made you host.
No, you made a.
I am.
Oh, you are. Okay. Can you get the screen sharing going? Anne?
Could you put
Yeah, I'll see if I can make it. Let's see, make co-host. Okay, Rivka, you should be a co-host.
Let's see.
Sorry
Yes.
for the technical. You got it? Okay.
Yep, I think so.
Sorry for the technical issue. Thank you. Okay, we see the screen, Rivka.
Okay, awesome. Well, thank you, Paul, and thank you all for being here. And I'm very grateful to be working on this with all of you. Civil estimating has taken me into some complex and unpredictable environments over the years. But the moon, that's a category of its own. When I started mapping cost estimating principles onto lunar conditions, just thinking about how it's done, the more I dug in, the more fascinating and also humbling it became. Everyone who has worked with ground condition knows this. Geotechnical borings are only a snapshot. The strata lines between them are never straight. No matter how much data you have going in, the ground still finds a way to surprise you. That's the nature of the work. I've built estimates on projects where the borings told one story and the ground told another. That is just another day for me. Now take that condition and move it into a space where everything gets amplified. There's no supply chain, there's no regulatory framework, no production records, and add 1/6 gravity to that. That's the moon. And that's why civil estimating is a good foundation for this problem. And that's what this framework does. Taking core civil estimating principles and mapping them against lunar conditions to identify where they hold, where they need adaptation, and where more data is needed to fill the gaps. Before I get into the framework of the paper, something from the Apollo transcripts that I read many of them, researching the writing for this paper. So something I read there really grounded this whole thing for me. When I was reading through the transcripts and the dialogue, I found something that stopped me. One of the commanders standing on the surface of the moon said that the terrain was rougher than he expected, more variability than the maps had shown. The environment will always know more than the model. So our job as estimators is to build a structure that holds that honestly. That observation shaped every domain in this framework as I was thinking about it and writing about it. So the framework has 8 domains. Each one is a place where the lunar environment forces a cost decision. So I'll just go through them, quickly, and obviously each of these domains is expanded on a lot more in the paper. So number 1 is scope definition. Every reliable estimate starts with a clearly defined scope. On the moon, that means identifying exactly where Earth-based logic holds and where lunar conditions force a different approach. Number 2 is regolith as a cost variable. The deeper you dig into the lunar surface, the denser and more resistant the material becomes. That shift drives every decision about equipment, production rate, and energy consumption. Number 3 is slope and safety. On the moon, safety standards have to be engineered from the ground up. We don't have OSHA on the moon. So every decision about slope angle, excavation depth, benching maybe, and wall stability has a direct cost consequence. There's no regulatory baseline to start from, so we have to decide everything as we go. Number 4 is material expansion and compression. This is a little bit of a complex one, even here on Earth. When you excavate soil, it swells. When you compact it, it shrinks. Those changes drive haul volumes, storage, equipment cycles, and backfill requirements. On the moon, we have limited data on how regolith behaves through that process. And that uncertainty carries direct cost consequences at every stage of the work. Number 5 is spoils as a life cycle cost. Excavation generates material that has to go somewhere. So placement, hauling, stabilization, and rehandling sometimes are continuous cost centers, not just one-time decisions. Number 6 is terrain variability. And this is also something that you could see a lot in the dialogue of the astronauts on the Apollo missions. And some very interesting dialogue that, we don't have time to kind of go through it, but I would encourage everyone to read it. To me, it was like just amazing to go through it, and you almost feel like you're there when you read it. So craters, buried boulders, uneven ground, every one of them is a cost variable that has to be priced. Number 7 is utility bedding and foundation support. On Earth, bedding materials are widely available and well understood. It's just one other thing on the job. On the moon, every cubic yard of material that either provides structural support or protects utilities has to be either sourced, processed, or imported. That changes the cost equation entirely. And finally, number 8 is ISRU versus Earth import. Every material decision is a value analysis. Process it in situ or ship it from Earth. Both scenarios have to be priced, including a fallback option. Uncertainty and predictive modeling. What do we do with that? So every estimate I've ever built has a production backbone. How long it takes, with what equipment, under what conditions. On Earth, that comes from decades of project records. You know what an excavator can do in a given soil type because someone has done it 1,000 times and written it down. On the moon, that backbone doesn't exist. The closest thing we have is NASA's prototype lunar excavator, and it hasn't actually operated in lunar conditions yet. So how do you build a production-based cost model when your only reference is unproven, autonomous, and still being tested? That question connects to something we already wrestle with here on Earth. The data problem. We build sophisticated models and then wait for the field to feed them. But the field is focused on something else. They're focused on execution, running equipment, managing conditions, solving real-time problems as they happen. Data capture is treated as an overhead burden unless it's designed into the system from the beginning. And here's the thing about production data. It doesn't exist in isolation. If you change one variable, whether it's cycle time, haul distance, excavation depth, you're not changing just one thing. You're changing the entire cost structure. On the moon, because the equipment is autonomous, that problem gets solved differently. data collection is engineered into the system from the beginning. So every cycle, every pass, every condition change feeds directly back into the model, not as an afterthought, but as a core function, which means the people designing that equipment and the people building the cost model need to be in the same conversation from the outset. A predictive estimating framework on the moon could actually be better fed than one on Earth. The model has to be built to receive it. That's what this framework does. So where this work lives in master theory in general. So every estimate starts as a prediction, a structured guess based on the best information we have at the time. And the moment work begins, reality starts talking back to us. The challenge, whether it's in construction and mission planning or anything complex, is to keep those two aligned. When they drift, you connect. And you keep doing that continuously, feeding the model with real data, tightening assumptions, narrowing ranges, until the prediction and the reality are so close, they're hard to separate. That's the goal. And that's what master theory is doing. It's a living loop. And the work in this paper defines the cost structure, the assumptions, and the production logic that allow that loop to function from the very beginning, before a single piece of equipment even touches the surface. So what comes next? There are many areas that need to develop for this framework to reach its full potential. 3 in particular stand out for me: equipment performance data, subsurface modeling, and integration with mission design. The one that keeps pulling my attention is equipment. How do we design systems that don't just operate, but generate the kind of continuous data a model like this depends on? Because every design decision carries a cost implication, and those belong in the conversation early. From my perspective, the estimating framework and the equipment design have to grow up together. The cost implication of those decisions show up long before anything gets built. That's where I keep landing. And I'd be very interested in how this room is thinking about that. Thank you. I'm looking forward to the discussion.
That's beautiful. Outstanding. So let's open up to questions. We have 5 minutes. Outstanding, both of you. Very profound thoughts. Rivka, I really appreciate that you tied it back to the estimating master theory. Outstanding work. And your paper's a joy to read, by the way. And
Thank you.
So, let's open it up for questions to the group. Yes,
Yabanka. So this is really
I'm
impressive.
sorry. I'm sorry.
Yeah, that's okay. This is really amazing. I really appreciate the structure that you gave to something that's so difficult to translate from Earth to the lunar environment. And it seems like we're on a hunt to capture that clearer and clearer. And every time I hear sort of a presentation on this, I get a little bit finer resolution on this picture, and I really appreciate the effort to make this connection. I was going to ask you what your thoughts are about the emerging conversations that are taking place concerning building digital twins, which are intended to create this live feedback loop and connect the equipment with data and then make adjustments on a real-time basis. I'm curious whether that will be the kind of framework that might apply here, or just what your thoughts are, just because we've been talking so much about it in our space here at NASA.
Question is for me?
Yes, or anyone.
Well, I mean, I think that's the way to go. So I haven't had the opportunity to be in contact directly with the people that are developing these pieces of equipment. So I'm in the dark as much as you are, probably more so. But I think that that is a very big component of all of this. And I am very interested in where this is going and how.
Thank you.
Yeah, yes. And if I could just convey that in the master theory with the engineering model and predictive models, uh, uh, model twins is what we determined to be a must. And not only is it a journey for this master theory, estimating theory, but it's also becoming a must in complex projects here on Earth for massive projects. And companies are spending a lot of time and resource to really have a full cycle um, uh, uh, digital twin that you can use that goes into maintenance and even decommissioning. So it's certainly a full cycle, and digital twins are a must because that's what maintains a predicted reality, and you don't get lost in what was predicted and what's the actual what was predicted and what's actually occurring. I'd like to defer also, Steve, this is kind of down your alley as well. You've been talking a lot about digital twins as well, Steve.
Um, yeah, but actually, first I had a question for Rick, and that was the existing, digital twins, models that we use for mining and tracking mining. Um, how closely, like, how well do you think those will work for the moon? Can they be adapted for that, or do we have a lot of gaps in that technology that we need to develop new techniques for?
I'm not familiar enough with that technology to be able to answer that.
Okay, yeah. Just some of the things that I've been working with at NASA are trying to meld some of the technologies that we'll need for the moon and start using them here on Earth to kind of modernize them and test them. And it's amazing how quickly we run into shared issues when we try to do stuff. One of that is just trying to set up the modeling system, and I can't find any standards for something that a robot could track and recognize. I just dug a hole in the ground, and now there's a hole there. Now, when I go dig, I'm going to need to go another further to dig that hole, that sort of thing. I assume it exists for mining and we can adapt it, but I just haven't seen it yet myself.
Yeah, but also, Steve, good point. But remember, we're the digital twins won't be just for mining. It will be for foundations and living habitat and manufacturing mechanisms that do recycling and converting, the machinery that converts the water into oxygen and hydrogen, on and on.
Oh
I'd
yeah,
like. Go
we'll
ahead,
need to
Steve.
model everything. I think one of
Yeah.
my assumptions is that we'll be adopting terrestrial standards to the greatest extent possible when we start
Yeah.
doing construction on the moon, because the construction on the moon looks almost identical to construction on Earth, just in a environment with some very different challenges.
Sure.
But as far as modeling goes, I would expect we'll use the same GIS, the same BIM. That we'd have to extend those to work on the moon. Like IFC will have to have a lot of extensions to work if IFC remains relevant once we start getting more and more sophisticated models.
Sure.
There's a lot of frontier work with the modeling environment that just doesn't exist yet, or exists in bits and pieces around.
Understood. I know we're going a little over, but if you wouldn't mind, I'd like to call on Jennifer Taylor, who's with HDR, a major architectural firm, and she's on mega projects, $4.5 billion hospitals, what have you, and she coordinates design and construction from the designer perspective. And I know that they do modeling of this nature. Jennifer, what's your thoughts on this?
Uh, Well, first, I just want to say I thought both the presentations were really fascinating. So,
Yeah, agreed.
just super cool. I didn't know, like the SpaceNet software where you can, be calculating all these different factors. So that, and then also, Rivka, I really think your 8 points that you laid out, like of, you know, honing in on what's important on terrestrial and then how that is going to play out really differently on the moon is super fascinating and great framework. As far as like digital twins, and things like that, I mean, I think we're modeling more and more in Revit on projects and getting more and more into detail. The UCSF project, for instance, it's not just us, it's the trades, right, who are modeling every back box and every stud and everything they want to build from the model. And I think figuring out how far to take that and is really important. It's like where at least on, construction on Earth, where's the sort of cost benefit to that,
The
if you
law of diminishing return.
yeah,
Right.
the law of
Yeah.
diminishing returns.
Mhm.
At what point is it just you're putting so much time into creating this amazing model, but then the model, our software still doesn't function that well when it gets that heavy and you can't manage it, and you're putting too much of that detail in there versus maybe other methods of that we need to develop of how to better manage that. As we translate from, design to construction. So I don't have any
Yeah.
answers for sure, but it's definitely something we're kind of.
Yeah, I think one thing that I had like an epiphany just a couple of weeks ago was that all these like the engineering design models that we create in BIM and these systems and the digital twins that we're building, they're not just related. They are literally the same model at different points in the system lifecycle being used for different purposes. And right now, they're disconnected because the way we build the construction model, or like we have different criteria, different purposes for it. So we're using that, and then when you need to go build a digital twin, like the construction model usually didn't have any of that stuff built in, so we end up having to import maybe elements of that data, but we create a completely different model for digital twins, and different aspects are using different digital twins, and I am anticipating we will see that converge as we get more and more automation, because robots aren't going to read paper drawings. They're not going to read PDFs.
Right.
If they do read a PDF, they're creating a mental model like on the fly. And if we create that sophisticated engineering model with everything included in it for construction, there's certainly benefits, for construction. Not the least of which is enabling automated methods to bring down the cost of construction. So, benefits here on Earth to reduce the costs. Absolutely critical path for the moon, because we're not going to be able to afford astronauts to build things on the moon the same way that we build on Earth.
One thing that like Rivka was mentioning, we don't have OSHA or other codes and regulations for building on the moon yet, and that's one of the things that when you talk about what we can continue to develop the technology for building that's more seamless from the model to building, but we still have to submit drawings to the drawing department, right? To the and a lot of our inability to modernize in architecture is based on the fact that we still have this deliverable to the authorities having jurisdiction and they're still on Earth tend to be, if not paper-based, at least drawing, two-dimensionally based. And that's a huge sort of double up of work effort.
Yeah, I mean, I think there's automated methods. If we have that model, like if we can just push a button and spit out the drawings that the regulations require, that's probably not that big of a lift. They're not necessarily going to need the same rigor that we actually need for construction. And if that's in the model, that's accomplished. And some of the other pieces, like I was worried, like the tools don't exist. Electricians and mechanics, they they're used to drawings. You can't just send them a model and have them build off it. But when I actually started experimenting, building like knowledge graph models representing electrical and piping systems, my concerns went away, because when I actually did the visualization, it was a drawing. It was everything I'm used to seeing on a drawing, but it was interactive. I could zoom in and out. I could, click on it and, open, close valves and see the states change. And it was fantastic. I think a way better way to convey the data. And as the stuff matures, I think it will very rapidly be adopted, just because it's so, like, I don't know. I saw the advantages sitting on my computer and wondering why we're not seeing this all over yet.
Yeah.
That's a good point. We have a comment from Ivanka.
Oh, I have another question, and I'm sure it's somewhere embedded in all of this, and that is, how can we use these tools to think of trade-offs between modularizing construction, pre-construction, basically bringing certain things already pre-built versus doing everything from scratch on the moon? And I know that that's kind of the ultimate battleground, is how do you decide what's cost effective and where's that optimal solution? We've been talking more here about large structures, assembling large structures in space, and because it's more economical. But is it economical for smaller structures? So I'm just curious, like, can there be research or some way of modeling that and looking for the optimal outcome based on a specific mission or configuration of infrastructure?
Yeah, if I may just take the first stab at that, there's something that is, and it of course in engineering, and NASA does this as well, as well as other engineering firms, is generative design, which is going through all sorts of scenarios, and we're starting to use that more and more on complex projects here on Earth to find out, because modular is becoming more prevalent in complex here in Earth construction, efficiency of time in production. And there's been discussion in our group with, you have to do a lot of experimentation to really decide how that is. And the complexity is you're not ordering the material out of a catalog. It's being manufactured for a very specific purpose. And so I think that's just one of those tie-ins to the estimating process that has to be part of that generative design to find out. Because what we've also determined is it's not necessarily after launch, and it's a payload, then it's not necessarily about your cost of material, because it's insured once it's a payload. It at that point is cost of resource and production. It's time. So I think it's something that is through generative design or whatever process is thought about. I think that needs to be a very active part of determining efficiency of cost, and because that also ties in not only the cost to manufacture, but also cost to produce, to actually install. And I know we've had a couple discussions. Is do you put the modular units together in moon orbit and then land it? Because it's 1/6 gravity. It's not like you have to go, burn up in the Earth's atmosphere. And so there's all those type of things that I could see all sorts of opportunities for predictive modeling. And I think the key, though, when we come to estimating, is it really has to be a synergy between prediction of cost and design, and that generative design, not only for efficiency or performance, but also cost and time. But anyway, you bring up very good points. Really appreciate you joining us today. Thank you. I'm looking at the time, and Are there any last thoughts? And I think I was very thrilled with the presentations today. They were both of them were just absolutely outstanding, very thought-provoking. Any last words from anyone? Not
Thanks
last, but
so much
parting
for
words.
thanks so much, you guys, for having me here today. Ivanka, in response to what you had just kind of talked about, when I had been doing some of this work with SpaceNet, I was in collaboration with the space logistics team at Blue Origin. And a lot of the stuff that we looked at was the challenge of deploying things from the lunar landers, getting them out of the lunar lander and onto the surface. There are some images and renderings of the containers and how they will be transported off of the lunar lander. And it looks like it's not extremely well fleshed out yet. It looked like a challenge for the astronauts to try and get things off, and it looked heavily constrained by the size of the doorway to get out of the lunar lander, but also just the size of the payload space of the current landers and the planned the size inside Orion, for example, or inside Gateway and things like that. And so a lot of the things that we had considered for like a surface habitat, for example, is like making it built out of an inflatable structure, and delivering it that way or things like that. But yeah, like just to bounce off of what you said, like the most expensive part that I saw from my models was crew transportation to the lunar surface. And they need to bring all the supplies that they need with them, to sustain them while they're there, and commissioning and assembling these things. But yeah, there's like that bottleneck of, if you send something fully deployed, if you wanted to do that, can you even get it out of the lunar lander? Some of these things. But yeah, just my parting thoughts. Thank you guys again for watching.
Yeah, another conversation.
If you don't mind, to Ireland,
Yeah.
Matthew Mullen is heavily involved in some of that research, actually like building the lunar crane and testing that. And he is part of this group. I don't see him here today, but I think we can definitely get some of those questions answered to see what the
That'd be great.
As far as I
Yeah,
know, it's very successful. I was just in their lab like Thursday looking at it and
That's so cool.
running some tests. It was pretty cool.
Wow, that's exciting.
Hey, Steve, if you can reach out to him, because I could see a discussion, a deep discussion on this topic specifically, because that gets into pre-con and how we, even articulate an estimate.
Yeah, and he's done some actual cost estimation on this that unfortunately isn't public.
Oh, that's beautiful.
It's using a lot of internal NASA data, but I think it'll be very valuable for him to speak to the group, and if he's able to share what he's done.
Yeah, that'd be wonderful.
It's just so complementary with like what Ireland is doing and what Rivka just briefed, and so many people doing different bits and pieces, and all fits together to.
Yeah, that's beautiful. Yeah. Well, with that, thank you so much. I'm looking forward to you reaching out to him. I know he's part of the group. I didn't see him on for today, but I think he wasn't able to make it because he responded. Now that I think about it, but hey, thank you everyone. What a very productive, fun discussion, and I look forward to these meetings every week, and they're very thought-provoking, and they're not only relevant for lunar construction, but they're also relevant for Earth construction as well, because we're finding out new ways to do things, and that's just exciting. That's very exciting. One last thing, again, congratulations to Ann Liu, who was a student observer in this group for a year and a half, and takes care of the data page. She now works for Turner Construction, and um, uh, and uh, And I'm looking for one other gentleman here, if he's still here. Yes, Ashik, who now works for Swinnerton Builders. He was also a student observer in this group for a year, and they've gone into some great firms on the estimating side. So we're very proud of them. So both of them. All right, everyone have a great week, and we will see everybody next week. Thanks for everybody's contribution. Great presentations today. Bye-bye.
Thanks, guys.
Thanks, everybody.
Bye.